Hello and welcome to a new CNCM lecture, and this lecture is going to be on modular arithmetic, and this is going to be a three-part lecture, and the first part is going to be on congruences and their properties. So let's get started. So what is modular arithmetic? So if you're new to modular arithmetic, it's a way for us to display remainders and do mathematical operations with remainders. So how do we use this? Well, let's take, for example, 16, and we'll take it modulo 5. So what this quantity is showing us is, or asking us to find, is what is the remainder when 16 is divided by 5? Well, we know that we can write 16 as 3 times 5 plus 1. So this would be congruent to 1 modulo 5. So 16 is congruent to 1 modulo 5. And this is the most basic way to interpret modular arithmetic, just as math with remainders. However, there's a lot more to these congruences, which are denoted by the three lines. You see there, not two. Um, it's just a notational thing. This is the notation you use, if you're wondering. But there's a lot more than that. So, for example, 16 is also congruent to 6 mod 5. And you'd be asking, well, hold up. Why is 16 congruent to 6 mod 5? Isn't the remainder 1? Well, it turns out you can add 5 in modular arithmetic to a congruence without changing its value. And we're going to explore some properties like this that shows how you can use modular arithmetic and all the operations within it on problems. So let's go ahead and look at some properties. So first off, let's look at congruences as a whole. I already explained this kind of, but here's a more of a formal definition for congruences. So we say two integers a and b, which can be negative, are congruent modulo n, where a minus b is divisible by n. We write this as a is congruent to b mod n, and another way of thinking about this is that a and b have the same remainder when divided by n. If you go back here, 16 has a remainder of 1 when divided by 5, and 6 has a remainder of 1 when divided by 5. So this makes sense in the terms of the definition. So as we go on here, uh, note that if a minus b is divisible by n, then a minus b is a multiple of n. I don't know if I mentioned this, but let me read the first line again. We say two integers a and b, which can be negative or congruent modulo n when a minus b is divisible by n. That also means they have the same remainder, and we'll look more into this property later. So note that if a minus b is divisible by n, then a minus b is a multiple of n, which means that there exists an integer k such that a minus b is equal to k times n. Adding b to both sides, we have a equals b plus kn. So first of all, let's look at this. So we're given that in the definition that if A is congruent to B modulo N, that means A and B have the same remainder when divided by N, or N divides the difference A minus B. So we use this notation here, just a solid line to show that something divides something else. So in this case, N divides A minus B. If this here is true, then the congruence holds. So looking at the last line here, it tells us that some things here, a minus b equals k times n, which just shows that n divides into a minus b. But we'll look into more later in this lecture. So let's go on. So there's obviously, I'm here to explain to you the properties of this, and we're going to prove some of these properties to show that we can do all these operations in modular arithmetic. And I'm just going to say that you can add, subtract, and multiply in modular arithmetic, but you cannot divide. And division in modular arithmetic, or so on, quote unquote division, will be covered in the next part of the lecture. So here's property 1.1, the reflexive property. A is congruent to A mod n. Well, this is easy to see. We have that A is congruent to A mod n. That means if this is true, that means n must divide its difference, which means that n divides A minus A, which means that n divides 0, which is true, and any number divides 0. So this property holds. Property 1.2, a symmetry, A is congruent to B mod n if and only if B is congruent to A mod n. I'm going to show you just one direction of this if you're wondering why I don't prove the if and only if. If you don't understand what I'm talking about, you can just disregard it. But A is congruent to B mod n if B is congruent to A mod n. We'll consider it like that. So if B is congruent to A mod n, that means n must divide their difference, which is B minus A. Well, let's look at the congruence. A is congruent to B mod n. That means that n must divide A minus B. However, we can write A minus B as negative B minus A. So this is equivalent to saying that n divides into negative B minus A. Since we know that n divides into B minus A, this holds. So thus we have proved property 1.2. Let's move on. And property 1.3, transitivity. And so if A is congruent to B mod n and B is congruent to C mod n, that implies that A is congruent to C mod n. It's the same thing as saying if A is equal to B and B is equal to C, then A is equal to C. That's a property in this normal equalities. That's the property of transitivity. So let's prove it for modular arithmetic here. So let's keep this the way this is, but we've proved the property of symmetry. Not there, there. So we can rewrite this here as C is congruent to B mod n. And you'll see why in just a second why I did this. So this congruence tells us that n divides A minus B. All right, and this congruence tells us that n divides C minus B. Well, if n divides each of these, then n also has to divide their difference. That just makes sense logically. So let's see what that gives us. So we have n divides A minus B minus C minus B. This returns A minus C since the B's cancel. So we have n divides A minus C, which tells us that A is congruent to C modulo n. All right, let's go into some other properties here. Property 1.4, additivity. If you add a constant k to both sides of a congruence, will it still hold? And in this, we assume that A is congruent to B mod n. So let's look at this. This tells us that n divides into A plus k minus B plus k. Well, that is clearly true. Um, so we just have to simplify it. So this tells us that if this were to hold true, that is. Hmm. This might be using circular reasoning. Let me start over. Sorry for confusing you. Uh, I think this is fine. Sorry. So yeah, let's say that if this equality were to hold true, that means n has to divide the difference. Well, that gives us n divides into a minus b, since the k's cancel. And we know that since because of this congruence, so thus this is proven. Hold up 1 second, I'm just gonna check some things. All right. Property 1.5, scaling. K times A is congruent to K times B modulo N. So let's just say that A is congruent to B mod N. Well, if we're trying to show that Ka is congruent to Kb if A is congruent to B. So let's see that all I have to show is that N divides into the difference, which is Ka minus Kb. Well, we can factor out a K here, which gives us N divides K times A minus B. Well, we clearly know that uh, from this congruence over here. So this is proven. Since n divides into a minus b, n obviously has to divide into k times a minus b. So this is proven. Property 1.5. Property 1.6 addition. A1 plus A2 is congruent to B1 plus B2 if A1 is congruent to B1 and A2 is congruent to B2. So let's look at this. Well, if this were to hold true, that means we have to show that their difference, n divides into their difference. So A1 plus A2 minus B1 plus B2. Well, now let's actually subtract this. This is going to give you n divides, and we can actually group this A1 minus B1, and then plus A2 minus B2. We know that n divides into A1 minus B1 because of this congruence right here. And we know that n divides into A2 minus B2 because of this congruence right here. So n must divide into this sum, and thus we have proved property 1.6. Property 1.7, subtraction. So this is similar to addition, but you just have a negative. You're adding a negative term. So I can just go ahead with this proof to show you. N divides A1 minus A2. Also, this is assuming that A1 is congruent to B1 and A2 is congruent to B2. So let's continue. So for this to hold, we have to show that n divides into the difference, which is A1 minus A2 minus B1 minus B2. So we can simplify this down. This is once again going to give you n divides into, there's A1 and negative B1, so A1 minus B1. And then we have minus A2 plus B2. So what I'm going to do is, since that's going to give us a negative of uh, what is A2 minus B2, I'll just write it out. So this gives you minus A2 plus B2, but that here can be written as negative A2 minus B2. So if we can also go ahead and just change the sign there. We know that n divides into A1 minus B1 because of this congruence right here, and n divides into A2 minus B2 because of this congruence right here. Thus, n must divide into the difference, and we have proved property 1.7. Property 1.8, multiplication. So what you have to do here is you have to show that n divides into, also this is assuming that A1 is congruent to B1 and A2 is congruent to B2. Well, we have to show that n divides into A1, A2 minus B1, B2. So let's find a way to rewrite A1, A2 minus B1, B2 so it involves differences of our initial terms. It turns out that A1, A2 minus B1, B2 is equal to B2 times A1 minus B1 plus A1 times A2 minus B2. Okay? Well, n must divide into this. We know that n divides into this original term, so it's a constant multiplied by A1 times B1, which we know that n divides into because of this congruence. And similarly for the other congruence, we show that n divides into this as well, which means that n must divide into this whole statement, showing that n divides into a1, a2 minus b1, b2 over here. So we have proven property 1.8. Property 1.9, this is luckily short for us because I don't have to explain it. We proved in property 1.8 that we can multiply in modular arithmetic. So also this is assuming if A is congruent to B. I have to make this clear and everything. This is just repeated multiplication. This is A times A times A and so on. K times, and that's the same thing for B. And so it's just repeated multiplication on both sides. So it's just something that follows from property 1.8. So we've proven that. So by proving those properties, while they may seem insignificant, they actually show that we can do several operations throughout modular arithmetic with addition, subtraction, and multiplication. And as I said, division is different in modular arithmetic. We'll look into that later in the next part of this lecture. But for now, we have some problems relating to this first part of the lecture that I'll cover. So let me go on. All right, problem 1.1. Find the value of x in each of the following congruences. So we want to find a value of x such that 0 is less than or equal to x is less than 3. And what is 62 congruent to modulo 3? And this all comes back from the first part I was explaining in the lecture. We just had to find the remainder since, well, they've bounded it here for us just to be strictly less than the modulo number, or n in this case. So let's look at 62. What's the remainder when 62 is divided by 3. So this, I'm just going to say that 62, since it's a smaller number, it's equal to 3 times 20 plus 2. So it is congruent to 2 modulo 3. 153 modulo 7. Well, this I can also write since it's a smaller number. Note that 7 times 21 is equal to 147. So this is actually 153 equals 7 times 21 plus 6. So that is congruent to 6 modulo 7. 1, 2, 3, 2, 1. Okay, I have to break out long division for this because it's not a small number, so I don't know what's going to divide into. So hopefully long division will give us the remainder. So 13 divides into 123. Oops. Can I remove that? I don't think so. Let me erase it real quick. Okay. So 13 goes into 123 9 times, and so 9, 117, 62, and 13 goes into 62 4 times, and so we subtract by 52 here to get 101, and 13 goes into 101 7 times, so that would be minus 13 times 7, which is 91. So that is going to give you a remainder of 10. So that is going to be congruent to 10 modulo 13. Let's move on here. So find the value of x if x is congruent to 11 to the 1, 2, 3, 4, 5 power modulo 12 and 0 is less than or equal to x is less than 12. Okay, this seems intimidating at first because why is there such a big power? Well, think about negative integers for simplification. Well, let's take a look at negative integers. Well, thing here is, let's say if we got that 11 down to a 1 or a negative 1, then we can easily take the power. Well, as I've said before, since 12 is congruent to 0 modulo 12, adding or subtracting 12 from either 12 or a multiple of 12 from either side of the congruence will not do anything. So let's say I were to take x is congruent to 11. 11, if I subtract 12 from it, is equal to negative 1. So this is also congruent to negative 1 modulo 12. And now you can see why modular arithmetic is so powerful. If you had the problem 11 to the 1, 2, 3, 4, 5 divided by 12, find the remainder, you'd be like, how would we even begin? Like, how would we even start on this? But now, with modular arithmetic, you have a much more powerful tool on your side. So now we can rewrite this as x is congruent to negative 1 to the 1, 2, 3, 4, 5 modulo 12. Well, since 1, 2, 3, 4, 5 is odd, this is going to be congruent to negative 1. And since they want something from 0 is less than or equal to x is less than 12, let's add back 12 so we have that. So that's going to be congruent to 11. So the answer was just 11. And that's all I have today. Please join our Discord at, well, this link is outdated. I will update it. I mean, you can't even access it from here, but I will post the link to our Discord in the description. Please do join if you need any help with this lecture or any content in this lecture. Please don't hesitate to ask us in the math help channel on our Discord server. And we also appreciate any feedback you have on this presentation and suggestions. Um, I will be making a part 2 of this lecture, so please stay tuned for that. Thank you for watching.